And today I'll talk about our work on cuprate superconductors, and in particular, focusing on the pseudogap phase. So I'll be mentioning the work of, in particular, 4 members of my group. So Nicolas Doiron-Léraud, a research professional, Gaël Grissonant, a postdoc who just left the group, Anaël Legros, who's now doing a postdoc with Peter Armitage, and Marie-Ève Boulanger, PhD. So in particular, Gaël's been leading the development of a new technique for us, the thermal Hall effect, which I'll talk at the end. It's really been quite an amazingly successful project. So here's a typical phase diagram of cuprates. I won't talk at all about charge density wave order, which occurs sort of in the middle of the pseudogap phase, but I'll focus on the end point of that phase where T star goes to 0, in particular, in the absence of superconductivity. So we're going to suppress superconductivity with a large field, and therefore everything you're going to see is in the normal state, hopefully as low in temperature as we can get, as close to T plus 0 as so I'll touch on 5 signatures I'd like to mention of the pseudogap phase. So a drop in carrier density, or a recent study of the Fermi surface using angle-dependent magnetoresistance. It's in collaboration with Brad Ramshaw. Field linear resistivity, evidence of a limit on the position of the quantum critical point, and finally thermal Hall. So one of the materials we've studied a lot is neodymium doped LSCO, and the main reason is that TC is low. So TC is 20 Kelvin, and as a result, we only need static fields to suppress superconductivity. We don't need to go in pulse field lab. And it's also very well defined as a very well defined T star line, which we can detect by measuring, say, resistivity. Here you see at 24%, nothing happens. There's a nice linear T behavior. I'll come back to that. And the signature of the pseudogap opening shows up as an upturn in the resistivity. So this is a gradual process. It's not a sharp transition, but you can sort of pick out a T star around 50K or so at that doping, and that's this point here. So you can do this as a function of doping. But the nice thing about the system is that RPAS was done on the same material, the same doping, by Johann Chang in Zurich. And so you see the antinodal pseudogap at different dopings, 12, 15, 20%, but not at 24. So sure enough, you didn't see any signature of it, and they don't either. The 24 is just above the critical doping, which is 23. If you see it at 20% and look at the temperature dependence of the RPAS, you see that this gap closes at about 75K or so, and that's the square there, which matches very nicely the onset of the alternative. So transport and RPAS agree very well. We know where we are in the phase diagram. So let me come to the first signature I'd like to highlight, and that's at low temperatures as we cross into the pseudogap phase. And that's the Hall number. The measurement is the Hall coefficient, and that's just 1 over the Hall coefficient in proper units. So this is in carriers per copper. And now, so our original measurement was on YPCO, done with Civil Post in fields up to 90 Tesla balloons, where we suppress superconductivity. Then we redid this study with lower fields, say 33 Tesla. That's enough for NDLSCO, with a very, very similar drop in carrier density from 1 plus P to P. And recently, Tony Carrington and Nigel Hussey have done this kind of study in pulse field on dying control. And they go from 1 plus P to P as well. So this signature of the pseudogap is really becoming generic in 3 very different materials. And so we think it's telling us something very important about the thing. You're losing basically 1 carrier per copper as you go from above to below. Of course, we'd like to know what the Fermi surface really is. At the moment, RPAS tells us it looks like it's Fermi arcs. Is this an effect of being at high temperature or strong scattering? So our take on the Fermi surface has been to use a technique called ADMR, angle-dependent magnetoresistance. And studied this very same material, neodymium LSD. So this is a close collaboration with Brad Ramshaw at Cornell and his student Yawen Fang. And in my group, it was really Gael who led this effort together with Anaël. So the ADMR, I won't go into great descriptions of what it is, but basically it's a measure of the resistance along the C-axis in a field that you tilt in two different angles. And as you tilt the field, as you tilt the field, you basically generate orbits around the Fermi surface, and those orbits give you orbital magnetoresistance, which will depend on the average velocity around that particular orbit. So in the end, you're basically mapping out the topology of your Fermi surface. And the guy who really pioneered this is Michael. In 2003, produced a very nice study of thallium-201 overdose. And he was able to map out in detail what the Fermi surface was of thallium-201. And that then got perfectly reproduced by RPS and quantum oscillation. So all these wiggles contain detailed information about the size of the Fermi surface and the KZ dispersion, and also the dependence in the plane. So we basically decided to do the same experiment. And I'm going to show you data for two dopings on either side of the feedstock, the 24 and 21. Okay, so here's the raw data as it comes out of the experiment. These are experiments done at Tallahassee in 45 Tesla. You kill superconductivity and you tilt the angle with respect to the C-axis. So here is the field is parallel to the C-axis, and then you tilt it in the plane. At 90 degrees, you're in the plane, in the copper oxide. So what you see immediately is that the ADMR at 24% is completely different from the ADMR at 21. So if this is telling you about the topology of the Fermi surface, then that topology changes. Okay, so we've got our hands on the Fermi surface change across these stuff. So I can show you that on this side, we have a detailed understanding of all these curves and all the wiggles and all the details, given the RPS determined Fermi surface. Okay. So again, going back to the work of Johan Chang in two papers where they measure in-plane and also the C-axis dispersion, we know extremely well what the Fermi surface is as a function of kz. So if you take the parameterization of the Fermi surface in terms of T prime, T double prime, T z, and you just take it right over and you calculate in the Chambers formula what do you expect for the ADMR, then that's what you get. So this is the data, these are the calculations at different temperatures, so 25, 12, 20, 12, and 6. You lose the data at low temperatures because the in-plane is not enough to kill it. But the only thing that is a fitting parameter here is the scattering rate, or tau, the relaxation tau. So we don't know tau. You put it in as a simple function of angle, of the phi angle, and that's what tau comes out to. So tau is strongly anisotropic. The reason for that is that you're very close to Van Hoek singularity. And at that point, the density of state becomes large and scattering rate becomes large. So tau becomes small. But then you can get tau out to different temperatures. And the beauty of it is that it is a measurement of tau. You know, essentially orbital magnetoresistance is omega c tau. So here you're getting a temperature dependence of 1 over tau, so h bar over tau. And what you see is that you get a linear dependence of the scattering rate, and it's of order kBt. Oh, this should be T. So it's of order kBt. And this is all this business of Planck anticipation. Why is it that the scattering rate is of order kBt? So I'll come back to that in 2 seconds with this particular contribution from Anaël, published last year, where she did measurements of resistivity on bismuth 2212. So it's been known for many years that the lower TC systems like bismuth 2201 or LSCO have these linear T dependence of the resistivity. We wanted to check that in the high TC system, this is also true. And so that's her work here at Toulouse in high fields, suppress superconductivity at the highest doping we can get our hands on. and she saw a beautifully linear resistivity in the normal space. And the thing that struck us at the time is that the slope is actually the same as what we saw in NDLSCO. These are very different systems. At comparable doping, they have the same slope. So what is the meaning of that slope, in other words? And that got us to eventually realizing that the slope is controlled by the so-called Planckian limit. And so now we have 7 different coupe rates, including electron doped coupe rates, where if you try to estimate tau, and sometimes, you know, it's a bit of a, it's not that easy, you do the best you can and you pull out a coefficient alpha, which relates scattering rate to temperature, which is a border. Now the ADMR is nice because it's the first time that we have a more or less direct measurement of tau, as opposed to extracting it from, say, the Euler formula and using the math or quantum multiplication. Okay, so this whole physics of the T-linear resistivity, of course, connects very nicely with twisted bilayer graphene that we heard about this morning, and particularly in Alan's talk. And that's what Pablo sees in his samples as well. He sees incredibly linear temperature, down to very low temperature, down to TC basically. And that slope is of order, I think you get 1.3 or 1.48. So there's a nice connection between coupe and twisted bilayer graphene on that particular issue. Okay, so let's get back to ADMR then, and what do we learn about these very different curves on the pseudogap phase side? Well, what you have to do here, since you don't know the Fermi surface, is to try different things. So in a short, to make a long story short, we tried 3 different things. One, you don't change anything, you just change the doping and you go through the Van Hoff singularity. So you go from electron-like Fermi surface to hole-like Fermi surface. That doesn't do anything, actually, because all the action is at the antinode, and that's where Fermi velocity is. So that doesn't do anything. You can try charge order, as in YBCO, where you get these small electron-like pockets. That gives something very, very different from what you see. If you see a large sheet at pi angle, you see a bit. And finally, we tried hole-like pockets, as if you had antiferromagnetic orbit. And that more or less works. That seems to work. So at the moment, we would say that if anything, what the Fermi surface looks like is these small nodal hole pockets. Okay, so that's for the third signature I wanted to mention, for this access to the Fermi surface. And now I want to mention an interesting fact that we stumbled upon experimentally that was actually understood theoretically by the work of Antoine Georges and Michel Ferrero and their group in Paris. And that's the following idea, that I'm not going to go through the whole talk, but basically by applying pressure, I think I showed some data. A tiny amount of pressure, 2 GPa, for those who know about pressure, it's small. You're just tweaking, these are hard to do. Just tweaking the system, you dramatically go from this large upturn to absolutely no upturn. So you basically mimic what you do with doping. So you can do with pressure what you do with doping. In other words, pressure actually shifts the pseudo-gap critical point. And how can that be? Well, what we worked out is that what you're actually doing is you're shifting the Van Hoff point. So you're pushing the Van Hoff point down in doping. And so that's what I call PFS, the P26. And so pressure moves this down, and P star is sort of forced to follow. So we came up with this inequality. P star has to be less than or equal to the Van Hoff point. And interestingly, in the work of Antoine's group, they did a calculation where in the Hubbard model, putting in the interactions, they saw a very large renormalization or shift of the line at which you expect to go from hole-like to electron-like. In other words, the Van Hoff point actually is affected strongly by interaction. And what they found is that by looking at where the pseudo-gap happens, indeed, it always happens below the Van Hoff point. So they also arrive at the same inequality. In other words, it appears that you cannot have a pseudo-gap if you have an electron-like Fermi surface, which doesn't cut the antiferromagnetic free one. It's an intriguing fact about this. Okay, and so for the rest of the talk, I'm going to talk about this thermal Hall results that was published last summer, where Gael, he basically discovered that the cuprate, even the mod insulators, so the cuprate mod insulators at zero doping have a huge thermal Hall signal. By huge, I mean, in fact, the largest ever seen in any insulator, whether it's spin liquids or, so where the hell does that come from? So that was completely unexpected. And so we're in the process now of trying to understand where this thermal Hall comes from. So thermal Hall, for those who don't know, is the thermal equivalent of the electrical Hall. So you send a heat current along the x-axis, a field along the z direction, and you measure the transverse temperature gradient, temperature difference delta Qy. The kappa xy is given by delta Q. Okay. I can go over various checks that we've done if you want to know at the end of the discussion. But basically, this is a measurement that we've performed. It's hard because it's a very small temperature difference. But here's the data. So I'm going to take you through the doping phase diagram again, starting at the high doping on the same material here initially that we looked at. So if we go to 24% above P star, we are in the metallic phase. Again, this is in field large enough to show superconductivity. And if we plot kappa over T, so kappa xy over T, this is the data. So it's positive, and it rises. And if you compare with the expectation from the Wiedemann-Franz law, L0 sigma xy, you see that it's very, very similar. And in particular, they match at low temperature, as you would expect of a metal. Okay? So in other words, everything is completely expected and normal at that doping. If you decrease the doping now into the pseudo-gap phase, where the green line is, so at 20% doping, things are okay at high temperature, above T star, but then at low temperature, things completely separate. And basically, a negative signal, a negative contribution kicks in. So when we saw that, we wanted to know, well, let's go lower and lower in doping and see, try to track that. And basically what we found is that it just kept growing as we underdoped all the way to zero doping. So this is an example at 8% and 6%, these two lines here. And you see that electrically, the stuff is basically an insulator. There's no charge response, but there's a huge thermal Hall signal. So this tells you that it cannot be the electrons that are giving you this negative thermal Hall signal. Also, if you, the bands here are meant to show where we see the negative signal, and you can see that it's always outside of this gray region, which corresponds to where you have static magnetic moment, as detected, say, by NMR or USR. So that tells you already that it's not, you don't need magnetic order to generate this thermal Hall. So it's not magnons, for example. And one nice way to see it is we can compare inside the magnetically ordered phase and outside, and you see the signal is very good. It doesn't matter if you don't, it doesn't care whether you have magnetic order. That's not to say that spin degrees of freedom are unimportant, but it's not the order actually that matters. So then what about phonons? Phonons carry heat. Can they generate a thermal Hall effect? And so to explore that possibility, we have this very simple idea that instead of sending the heat current in the plane, we're going to send it normal to it. And basically, the only thing that carries heat reasonably well, perpendicular to the copper oxide plane, are the phonons. Magnons are 2D, and any electronic excitation you can think of would be definitely more mobile in the plane than perpendicular. So we do basically J parallel to A and J parallel to C in the same material. So that's what came out at zero doping in La2CO4, in non-insulator. It's basically the same. It doesn't really matter, actually, whether you send the current in the plane or not. So that immediately led us to conclude that it must be the phonons that are actually carrying the heat and are responsible for this thermal Hall. This is beautifully confirmed by going up to 24%. So again, just outside of the pseudograph phase. This was the in-plane data that I showed you already. Now, out of plane, so kappa ZY, absolutely zero. So this tells you there's no phonon Hall effect at high doping, which is, of course, what you expect of a normal method. You don't expect a Hall effect of phonon, and sure enough, there's none. It's absolutely zero. I don't think I've ever been so happy to see zero in my lab, but because partly also it actually shows you that you've got the background completely under control, and there's no security background, and it does then. It's sort of thing that you had to have if your Wiedemann-Franz law was correct. You can't have both. If you have Wiedemann-Franz law, you can't have phonon. That would necessarily violate. Okay, so then as soon as you go from 24 to 21, you move inside the pseudo-gap phase, the phonon negative thermal Hall kicks in. So it's really a property of the pseudo-gap phase. So something about the pseudo-gap phase makes the phonons go chiral. Completely new information. Never had that in mind. We still don't understand the mechanism, but it's extremely interesting observation. So this is the three dopings we did for the C-axis thermal Hall. 0 at high doping. It kicks in as you enter the pseudo-gap phase, and it grows as you go lower. So this is all written up in a paper we posted just a week ago. Now I'm going to show you some data that's not yet posted, where this is work done by Marie-Ève Boulanger. She's looked at 2 other Mach insulators to compare with Le2CO4. So just very briefly, this is the thermal Hall signal in the plane now, divided by temperature, and I put a minus sign just to put things on a positive axis. So all of these are negative thermal Hall signals, but I just put a minus. So that's what I showed you before at 0 doping. And now you can see these 2 other guys also have a nice large thermal Hall. Now there's many reasons why these comparisons are interesting. One of the reasons is that this particular hoop rate is perfectly tetragonal. You know, the thing about La2CO4 is that it has an orthorhombic distortion, it has domains, and it has tilted octahedra, it has spin canting, and each of these things actually could potentially be a mechanism you might think of to try and explain the. So by going to this system where you have no spin canting, no domains, and you have a perfectly tetragonal system, you see that this is not, those structural differences are not at the heart of the phenomenon. You can also go to Nd2CO4, which is also tetragonal, not orthorhombic. You might ask, well, what happens if neodymium has a large magnetic moment? Does that play a role? Well, you might think it does. You know, you go from 1 to 10, so there's a tenfold. This is 10 times larger than this. But actually, when you look at the longitudinal phonon thermal conductivity, it's also 10 times that. So actually, the thermal Hall here scales with the longitudinal thermal conductivity. So I don't, for some reason I forgot to put the slide, but if I could take the ratio of these two, and it's the same ratio in all cases. You can vary the thermal conductivity of phonons by a factor of 10, but the ratio is the same. This is other evidence that it's really a phonon signal responsible for the effect. Okay, so I think that's the end, and I'll stop you for questions. Right, yes, that's definitely something that strikes you when you see this. What's also striking is the same is true for kappa XX. You know, kappa XX, there's nothing magic about kappa XX. It's just phonon thermal conductivity, right? So the fact that this guy, we know that it actually eventually comes back down. It's just that it peaks at a temperature which is lower than these two guys. So this tells us something that structurally there's a difference in the phonon behavior that affects the location of this peak, but that structural difference is not what causes kappa Y, because it's the same kappa Y and all of them when normalized by kappa. But it's an interesting question. I still wonder why that is. One of the things that maybe is part of the explanation is that actually this system has a soft mode, a soft optical mode because of the orthorhombic transition. And so, whereas the other guys don't. So it's as if there's an extra phonon branch at very low frequency. But these are very low temperatures. So I don't know whether that's quantitative.
More question?
We'll go back to mention that for the linear stimulation.
Yes. Yep.
So there was some suggestions a couple years ago that I did. That you get scaling.
Yes. Yeah, we don't get that scaling in that particular system. It's based, well, it's actually the magnetoresistance is very small. I didn't emphasize the magnitude of the ADMR, but if you saw the y-axis, it's actually all less than 1%. All these wiggles are within 1%, but the temperature dependence is very, very large. So that you basically reach a limit where you've got T-linear and almost no magnetoresistance.
I want to stay on that same issue.
Yeah.
So you have angle dependence of temperature dependence, presumably. So
yes.
I assume the temperature dependence you've been talking about is nodal.
Yes.
Can you tell us what happens to off nodal or antinode to the temperature dependence?
There, at the antinodes, we fit gamma to get the white wiggles, and the sensitivity of the fit to the nodal value. It dominates completely because that's where actually all the main trust. So you can we have big error bars on the result at the antinodes. So at the moment, depending on how you fit, you get a lot of variation. So we're not, we don't do that. So it could be that it's angle dependent intrinsically, but at least in the nodal direction where the transport is dominated, it gives you that.
I'm wondering, do you think that this is property of fluids, or maybe to measure some other molecules like Taillefer have similar things that you would try?
Yeah. Calcium luteinate has a large.
Even larger, right?
Even larger. No, I think basically, I think this is open here.
Electron coupling is essential.
Electron
the question is with systems.
Yeah.
I don't know if they have large electron coupling.
I would say spin phonon. These are insulated. So
yes.
Electron coupling is a general sense, but I would say spin phonon coupling is probably the key. That's my hunch. No. Well, sorry?
You don't need the
So just get it from phonons alone. Yeah, but the question is about this.
So, but what makes a phonon acquire, I would say, chirality in the field?
Well, if it's an ionic solid and you put it in a field, there's this very curvature. So that's just phonons alone without it.
Right. And so, what in your view would make it switch on as you enter the pseudogap phase? So you would make that ionic character to change dramatically as you go across.
I don't know. I'm just referring to his comment.
But that's, just to come back, so I think actually now, my view is that we have to re-examine all measurements of thermal Hall in insulin. So in particular, thermal Hall is used in spin liquids as a potential probe of exotic particles like mayor and Aspen. But it seems very likely to me that there's going to be a phonon signal in those systems as well. So for example, getting a quantized value is very unlikely because you'd have to have 0 phonons on the lead.
Okay, you have 30 seconds.
Okay, 30 seconds. Let me get one thing straight.
Yeah.
So when you say the switch is on the pseudogap phase, you mean throughout the pseudogap phase, or do you need the ODP? You need to be in the regime where the resistivity is sort of localized.
I'm just comparing these two curves. It's completely 0 on this side, and it becomes large just on the other side. Right? And if The thing is that this is phonon, so I don't see why you do all these things.
But basically, my question is, do you need just to be in some insulating like regime? Or you get it? There is also,
Yeah.
So other to create a regime, you need to have a metallic resistance.
I see, yeah. Yeah, so you definitely lose carriers when you go from there to there. Maybe a factor 5. There's a loss of carriers, so maybe there's a loss of screening, maybe the ionic effects are getting bigger. But it's really almost, the thing is that this is not small, it's big. Or, yeah, well, to put a number, it's 100. So this is 100 times larger than a million. So it's a big effect that switches off.
Okay, let's thank Will again.